Okay. Now, my formal introduction. Welcome. Thank you very much for your interest. And I'm very pleased to see this broad audience and interdisciplinary audience. It's very stimulating for me. It's very stimulating for any teacher to be able to interact with students from different fields, different disciplines. And I really think that this is what is needed when discussing about climate change. I'm highly motivated I'm highly convinced of that. Climate change requires, in order to take actions, requires an interdisciplinary dialogue, an interdisciplinary discussion and cooperation. So I think we are moving forward. I think that with this audience that is very diverse, I think we are moving forward. So you can understand why I am really motivated to interact with you. And I want to say that I'm also very pleased if you attend in physical presence. As I said, I'm not really putting any constraint on that, but I'm really motivated to interact with you face by face, because I think, of course, the discussion gains something. It's clear. The experience that we had with the pandemics clearly shows that there are some good opportunities, very good opportunities by virtual interaction. And I would say that this is one of the few benefits that the pandemics brought, an advance of the technology, an advance of our attitude to benefit from virtual interaction. This is indeed a positive thing, but it's also true that when the discussion is complicated, when it's complex, when the discussion requires really interaction, then the physical presence, the physical interaction is you know, it's more productive. The topic we are talking of, it's really a topical issue today, and it's very complex. It's not easy. It may look easy. It may look easy because everything seems to be very clear. But when we come to the question, what to do or what should I do, this becomes very complicated. It's a mechanism that includes several links within several societal components, several disciplines. So it's, for instance, political sciences, politics, economics, environmental sciences, hydrology, water science. The feedbacks and links are very complicated, partially unknown. So the problem is really an issue. And I think for this reason, because it's an issue and because it is complicated, it's really a good thing that in the universities, in our education, we start to gain additional information on it. And here, this is important to say, we are talking about the science of climate change and climate actions. We are not talking about the communication. We are not talking about the social aspects of it, or to some extent, yes, but we are not talking about politics, for instance. And the reason is that we need to be very focused. And first of all, understand what is behind. We have to understand the science of it. We have to understand the physics. We have to understand the economics as a science, not as a strategy. And this is important that I tell you, because one thing is science, one other thing is decision-making and communication. They are different issues. So in communication, maybe that we need to focus on some aspects of it, of climate change. In science and in engineering, in economics, we need to focus on other issues. For instance, I give you an example, uncertainty. Uncertainty is essential when we come to design. So an engineer needs an estimate of uncertainty. In communication, we have to be very careful when we talk about uncertainty, because people may think that our knowledge is incomplete, is not really well-based, well-grounded. So we have to be careful of the many facets of climate change and science of climate change. And here we talk about science. Talking about science means, in principle, that we should be very objective. So my personal opinion in what I'm teaching shouldn't interfere with what I'm saying, because science, by definition, should be objective, should be based on evidence. This is the definition of science. Science is the investigation, the evidence-based investigation of natural processes or linked natural social processes, but evidence-based. And this is essential to say when talking about climate change, because you know, it's not easy to find evidence. And therefore, when we talk about science, we have to be very clear what is the evidence and what is still something that we are looking for. Okay, now after this premise, I would like to give some information on logistics. So first of all, let's forget about the program of the course, which is available on the web. So I don't think I need to remind you that we will talk about climate history and whatever, also because this is an evolving process. For instance, some of the teachers that helped me last year are no more available to teach, so I had to find other colleagues, and therefore the topics are a little bit evolving. But in any case, if you want a very general information, if you look at what is shown here on the screen, and let me emphasize it, and which is what is reported on the web, as a skeleton program, this is fine. Okay, more or less, we will move into this field with possible changes also driven by the time that will take to us to discuss each one of these issues. So this is the calendar of the lectures. Each lecture day is including 3 hours of lecturing, and if you agree, I would propose that we make a break after 2 hours, which means I propose to start at 2:45 up to up to 4:15, which is 90 minutes of lecturing. Then a break of 15 minutes, and then I stop at I start at 4:30, stopping at 5:15. There is an alternative solution, which is to make a break after 45 minutes, which means 2:45, 3:30, 3:45, 4:30, 4:45, 5:30. To me, it doesn't matter. Today, let's start, please, with only one break. But if you prefer, from the next lecture, we can make a break of 15 minutes every hour. It doesn't really matter to me. Usually, my experience suggests that the students prefer to finish 15 minutes in advance. So this is why I am proposing only one break. But it's no problem for me if you have a different solution to propose. I could also start at 2:30. My usual experience is that if I start at 2:30, several students are late, because most of us, also teachers, are used to the academic quarter. But again, if you have any alternative solution, at the start of the next lecture, you can raise your hand and make a proposal, and then we discuss all together. Good. In the calendar, there is, in many lectures, indicated professor to be defined. Actually, I think I will deliver most of the lectures, with the exception of probably 1 or 2. I will inform you in advance. I am inviting, using these days, an international colleague whom is very acknowledged in climate change to deliver a lecture remotely. And he's checking the agenda. And the same thing for another colleague that I invited to deliver the lecture in physical presence. And they are checking their agenda. So I will need to update just the name of the professor, not the dates, okay? I don't think there will be the need to change any of these dates. If there is something like I take a cold or I get a cold or something like this, I will let you know in advance by writing on Virtuale if I need to cancel a lecture or if I need to be substituted at the last minute, okay? If everything goes fine, we should finish, sorry, just after, let me see, 11 April. I'm not really sure if 11 April is, let me just make a computation. Yeah. April. Okay, we should finish soon after Easter. I was just wondering whether 11 April is Easter Monday. I don't think so. I think Easter Monday is 9, 10. Is 10. So why I put 11 April? I think this is a mistake. I'm sorry. It's not 11, but it is 17. Okay, this is a mistake. I realized just now. Okay, it's Monday, April 17, because April 10 is Easter Monday, and on Tuesday we don't have any lectures. So 11 April is not correct, and Monday 11 April is not correct. I'm sorry for that. I will make the change. Okay. Now, next thing. Tutorial documents. My tutorial are in form of web pages. Not all of them. Most of them are in the form of web pages. So let me just click on, for instance, on this one, climate models. Just one second. It's a web page which is like a book, okay? And it is particularly suited for your studies. So it is something that includes part, it is mainly narrative. At the end of the page, probably there is, let me check if this is the case, a PowerPoint available for download. Let me check, just one second, it's very long. Okay, here there is a link, download the PowerPoint presentation. Let me show you what happens if we download it and start it. Just one second. It's a PowerPoint presentation that I may use during the lectures, okay? And it's basically a summary of what is reported on the web page. What is the purpose of this PowerPoint? To use it during the lectures, because of course the web page is not really handy, okay? During the lectures, I cannot show on the screen something like, just one second. A page like this, you know, it's not easy to read. Much better if I use a PowerPoint presentation, okay, where there is, it is organized in the form of a slide. But when you prepare your exam, my advice, don't look at the PowerPoint. It may look more attractive because it is shorter to read. It may be useful to refresh your mind, but if you want to prepare the exam, you have to look at the book, at the web page, because on the web page you find the information that may be the subject of questions at the exam. And keep in mind that at the exam, which is in, I will give you additional details, will be a quiz. The only questions that you can find in the quiz are questions which are discussed and the answer is given in the web pages. There are no questions that are not discussed and answered in the web pages. So the web pages are enough without following the links. Why I am using web pages? Because it's very nice, because I can use links. But the links are just useful for providing additional information in this subject, not for preparing the exam. Why additional information? Because, of course, we are studying not only to pass the exam. Passing the exam is required, but we are studying for getting educated, for building our CV, building our knowledge, building our preparation well beyond the exam. Okay, so I give to you the opportunity to get additional information if you are passionate about a topic, if you think that this information in your field is important. So I think the links are very important, but it's up to you to explore them. There are several links. It's impossible that you open and read every link in these web pages. Not impossible. Nothing is impossible for you, but still very demanding. And so the links, I think, are an essential piece of information, but not for the exam. So you don't need to follow the links to reply to the questions of the exam, okay? Most of the links we refer to Wikipedia, and the reason is that I want to avoid any advertisement. I really make an effort on that. There are some links which open third parties web pages where you can find some advertisement. It happened to me also this morning. I opened a page with an advertisement, nothing particularly worrying, but still it's an advertisement. I don't like it, okay? Especially in education. But most of the links will refer to Wikipedia, and most of the links should open independent pages. Let's make an example here. I'm clicking on mitigation. Let's see if it opens, because yeah, you see another page, climate change mitigation on Wikipedia. By the way, in this topic, climate change, it's impossible to work without referring on the web. So I could have selected books, but they are not enough. It's too evolving, too quickly evolving. So we need to refer to the web. Of course, referring to the web, and I think it is the web is the best solution to get educated about climate change, also scientifically educated. Of course, the web has a big problem that is very, very wide, and it's not easy to get oriented. So by proposing these links to you, I also aim to support you in this selection. But beware that one of the most important skills that you have to earn today is to be very efficient in browsing the web. It looks like it's easy, but it's not actually. But there are some tricks in order to get efficient in making a selection on the web. And my suggestion for you, try to learn these tricks. And one of the tricks is to be able to recognize the sources of information that are referenced, like Wikipedia. Of course, Wikipedia may still include some imprecision, especially in the native languages, but in English, I think it is really a solid support. So this is one of the tricks. So look at the source of information. So you Google something. First of all, the first trick is to be able to use the correct keys in Google. And then you look at the list and you see maybe the third one is Wikipedia or something that you know, like IPCC, something that you know it's a solid reference, and then you click on that one. Otherwise, if you go just along the list, it becomes really complicated. Okay, so these are my tutorials, and you see several links here. Some of the links are not redirecting to web pages, but let's make an example. Last year, there was this lecture given by Professor Antonio Navarra, Avoiding to be Ambushed by the Future, and the link was redirecting to Virtuale, to the page where you can download a PDF. Why is that? Because the material is not copyright free. This is a big problem when you want to use open information, you want to disseminate education as an open information. It is my commitment. I like that everything is open, and this is why most of the lectures are given as link on the web, on my website, not through Virtuale, because Virtuale is not open. Virtuale is open only to the students of the University of Bologna, and after you are not a student anymore, you don't have access to Virtuale. So this is something that I really don't like, because I think that the information if we want to really if we want really to be effective, we need that the information is open, is accessible. So this is why I put everything on the web, but I can tell you it is extremely demanding, because everything you write on the web as an open information must be an original creation. So cut and paste is not, of course, admitted, but also the use of figures. And this is the most complicated thing. You have to remake any of the figures or to use material that is not protected by copyright. So during the years, because I started this open attitude in 2012, during the years, I learned more or less, because sometimes I don't understand, what is free, what is not. So everything is produced by the government of the United States, for instance, is free, can be reused. And everything is on Wikimedia Commons is free. But unfortunately, there is not much. So, I mean, in this case, some of the lectures, like the lecture of Professor Navarra, some of the figures are not copyright free. So they can be used for teaching. They can be distributed to students, but not as an open information. It is a reserved distribution. So some of the links will bring you to Virtuale, where you can download it. I think that given that this year I am teaching most of the lectures, probably the number of links that will redirect you to not to a closed information will be reduced. But for now, there is still something that you find redirecting to Virtuale. The list of the links is evolving. I'm not sure I will have time to cover all of them. And probably there will be something different depending on the replies of my colleagues whom I asked to deliver a lecture. Depending on their replies, there might be something new that is connected here, linked here. But to give you an idea, if you want to get an idea of what could be this course about, if you look at the links as they are now, that's fine. Okay, now videos. I have a playlist on YouTube. Again, I started to make videos, to take videos of my lectures and make them available on YouTube in 2012. So if you look on YouTube, you have 10 years of my lectures. It's a lot of fun. And most of them are in Italian, but in the past few years, the majority of my lectures are given in English. And I choose at that time YouTube because first it was open, and second, it was not possible to use any channel through the university in order to make videos available. Just for your information, 10 years ago, it looks like it was another world. In order to understand whether I was allowed to take videos of my lectures and put them on YouTube, it was really a long process. To answer the question, can I put the video of my university lecture on YouTube? And it is not a matter of resistance, it's just a matter to understand what is the copyright. And the first thing I was told is no copyrighted material should be put on YouTube. So this is why I decided to remake all my tutorials by using free material. And it looks like, as I said, it was a different world. Now there is no question. I can put the videos on YouTube. And I am continuing to use YouTube because for continuity, but also because I think still it has the nice feature of being open. The videos will be put in two channels anyway, YouTube and Virtuale. Why two channels? First, because Virtuale is the official repository of the university for videos of the lectures. So I don't want to miss this opportunity. Second, Virtuale doesn't have any advertisement. Unfortunately, YouTube, even if I'm not monetizing, of course, the clicks on my videos, unfortunately, a couple of years ago, started anyway to give, to put advertisement at the start of the videos. I apologize for that. There is nothing I can do. The only thing I could do is to change platform by taking another free one like Vimeo, but I'm not sure if they started to put advertisement as well, or if they will start. So I don't think it is a problem that can be easily avoided. And so this is why I prefer to keep the two channels. If you are bothered by advertisement, just go on Virtuale and you have the same videos without any advertisement. Okay, now let me talk about the exam. First, how many exams? This is essential because you are 200 students registered. So it's a huge number which requires some organization. And also for this reason, I kindly ask you, if you need to contact me, if you use the email, it may be difficult for me to manage the replies because you understand, if 200 students start writing emails, it's unmanageable. So try to minimize your queries, first of all, but of course, when you have a question, please use the forum in Virtuale. And please be patient if you have to wait a couple of days to get a reply. Okay, so we have to be well organized and efficient. So how many exams? I am committed to give at least 6 opportunities during the academic year. I don't have any problem also to make 7. But please note that I may have some problems if I am asked 12 exams, just to give you a number. So try to stick on the official dates. If you need an extraordinary exam, of course you can ask, but I hope you understand if I cannot really make myself available to make many more than 6 exams. So beware of that, please. And when I am planning to give these 6 opportunities, 3 before summer. First of all, let's don't forget the constraint. Okay, so I cannot make exams during the lectures period. I cannot make exams before the end of the teaching of the 2nd semester. So even if you close the lectures on April 17, I cannot make an exam before June 9 because there is this limitation by the university. Okay, and also during the academic year, I am asked to avoid scheduling exam during the lecture period. And there is a reason for that. The reason, first of all, this requirement is not uniform across schools. In engineering, there is this requirement. In other schools, I know that it's not strict. What is the reason? The reason is that I cannot find rooms during the lecture period, first. Second, if professors start scheduling exams during the lecture period, then it becomes a problem because the students cannot attend the lectures. Okay, so being aware of these constraints, again, 3 exams before summer, which means June 9 is a Friday. I propose that June 11 or 12, we give the first opportunity. And I will decide the date very soon. I cannot make it on Friday, June 9, but probably on Monday, June 12, I can. Okay. I need to book a lab for it because the exam is a quiz. So I am booking the labs now. I hope in 1 week the booking will be confirmed. So next week, or at most during the next 2 weeks, I can confirm you the dates. So let's make an assumption. June 12th is a Monday. And then another exam after 15 days, which means June 27, 28. Not really the last week of June because I am busy, but maybe first days of July or June 20. Okay, we will see, depending also when the lab is available. A third one, like mid of July, July 20, July 15, July 20. 3 opportunities. September, 1 opportunity, mid of September. The 5th one and the 6th one during the break between the 1st and 2nd semester. So maybe just before Christmas, the 5th one, and January, half of January, the 6th one, or 2 opportunities in January, depending on the availability of the labs. And these are 6, okay? Now, it happened last year that in September, students asked for a 2nd opportunity, and they said yes. Okay, I'm not strict on 6. So, I mean, I do my best to make yourself comfortable. How the exam works, it's a quiz. It's a closed answer questions quiz with no penalty, only 1 correct answer. Maybe several alternatives, not just 3. I started with 3, but then I made some practical experiments with only 3 alternatives. I realized by making many attempts, by just randomly picking up the answers, that in many cases I got a very good mark. So I decided that 3 alternatives are not enough, and then you will find 5 or 7 alternatives, but only 1 is correct. And there is no penalty. So if you are in doubt, you can just go by chance, okay? There is no penalty whatsoever, and I'm not looking in any way at your answers. I mean, I'm looking at your answer, of course, but I'm not making any assessment of how wrong your answer is, okay? The time will be 30 minutes for 30 questions. For your information, the best students take about 12 minutes to complete it, because several of the questions are very quick. Okay, so really 30 minutes is a good time. The questions have equal weight. There are some difficult questions, some easy ones. It is subjective. What is easy for me may be not easy for you, and vice versa. But they have equal weight. Okay, so it means that you have 1 mark for each question and 30 questions. So the mark of the quiz is between 0 and 30. But the mark of the exam is higher usually than the mark of the quiz. What I mean to say is that you don't need to get 30 to answer correctly all the questions. Usually people get 30 even with Laude, even if a couple of questions, 3 questions are wrong. It depends on the overall performances, because I think it is fair to compare. Important thing, the questions are not the same for all the students, and they are not given in the same order, even if they are the same. So just beware of that. I will repeat this before the exam, in order not to get you confused, because you may assume that you have the same questions in the same orders. Also, the alternatives are not given in the same order. But in general, as I said, this is not a big problem. And my suggestion is, when you take your exam, I think it is much more efficient to try to make it yourself than trying to get some connection here or there. You can check also, I mean, you can have notes. I'm not checking that you don't have notes with you, etc. But again, if you start looking at notes, I don't think it is an efficient strategy. One important thing, I'm sure that you know that the exam can be taken only in physical presence. Okay, it is a strict requirement by the university. I cannot make any exception myself on that. It's not possible to me. The only exception can be granted by the offices of the university. You may have a good motivation, but I have to defer you to them. If you have a good motivation, if you want to get permission for that, I tell you that in the first semester, I didn't have any experience. The university is very strict on that. Okay. Let me just look at the check 1 second. Okay, perfect. So, I mean, I think that's it. The exam, I forgot to say, in physical presence in a lab. So you will have to connect through the labs through the computers that are available in the lab. The exam will be here at the School of Engineering. And of course, you could, in principle, if you are in physical presence, but you prefer to take the exam on your laptop, you can do that. It's not a problem. Okay. My suggestion is to try to avoid it because, you know, in the lab, computers are connected with a wired connection, not wireless, and the wireless may fail. It is, I mean, it's not a problem. Even if there is a connection problem, we can, just 1 second. Okay. Even if there is a connection problem, we can manage. I can restart your exam, but still it's a bit of a... Once that the exam is finished after 30 minutes, within 15 minutes, I am able to give you the results. And you are allowed to accept it, decline it. Of course, you are allowed also to review the exam, even if last year I asked students, look, if you got 30, please don't ask me to review the exam, because during an exam, there might be like 100 students. So if everyone starts asking to review it, it means that we stay the whole day in waiting for your reply. But of course, I perfectly understand. If the result is not what you are expecting, you may wish to see the exam. And so it's possible also when there are many students that I ask you to tell me what is your preference in terms of accepting, declining, and then I may schedule a virtual meeting after a couple of days to show you the results. Okay, so your choices are accept the mark, decline it, or think about it. Okay, think about it means that I'm not registering the mark unless you send me an email and you tell me, yes, I accept the mark. Okay. In principle, there is no limitation on the number of declines. In principle, you know that I may decide, I have the opportunity to decide to limit the number of declines. I don't like it, so I prefer to make you completely comfortable. My suggestion anyway is don't try by chance. If you want a good mark, so if you want to get more than 25, I think you need to prepare the exam. If you try by chance, you may need to try 10 times before getting it. And so my suggestion is to make an effort to focus on your target and decide accordingly. Okay, decide your preparation accordingly. I'm saying this because this year I had a problem with some students. They declined many times, and at the end they asked me extraordinary exams because they were really not happy with the last attempts. So they declined like 25 in June. And then they tried again and again and again. And at the last attempt, they got less than 25. So they asked me to make another attempt. And I said, sorry, I don't have more time. I cannot make exams during the lecture time. So beware of that. I mean, I don't think it is a wise policy just to try and to decline and decline and decline once again. Of course, in principle, it's not a big waste of time because it's just half an hour. But on the other hand, you understand that it may be risky for you. Okay. The last thing that I would like to say is I will do my best to seek an interaction with you. And interaction means I will ask you several times, do you have any questions? I know that these strategies usually are not very effective. I mean, students typically are shy and they don't want to ask questions or whatever. So I just would like to tell you already now, try to make an effort to stimulate my interaction. The lecture becomes less annoying because, you know, sometimes when I have some questions I need to discuss with you because I don't have an answer that is ready. So for everybody, you give a contribution. It becomes less annoying, really. I understand that it's only me speaking. It becomes annoying, okay? And if you have also questions that you want to ask me offline, that's not a problem, really. Use the forum, ask me questions, and then we can also discuss one by one. This is a form of interaction that is more demanding, less effective to involve the other students, but still, I really would like to gain with you a reciprocal experience of interaction and education, because if you interact with me, it's an opportunity for me to learn a lot of things. And I tell you, it's not something that I'm saying just for your pleasure. It's a truth. I can really learn if you stimulate me to interact. And everybody learns. So just make an effort. So do you have any questions so far? No questions. Okay. I think I said everything, and if you don't have questions, probably I said everything, but in any case, the discussion is open. So we took the first hour for this introduction, which is fine. And so if you don't have any additional question, I would propose that we start with the first link. Can I ask you one thing before we start? I know that there are some students in the audience who are attending the other course that I am teaching, which is called the Climate Change Adaptation. It's a course at engineering. Raise your hand, please, if you are attending also the other course. Nobody? Strange. But of course, not everyone is here. Okay. No, I am interested because there is some overlap. For instance, the introduction is the same. I did the introduction in the other course this morning. So I just wanted to say that there is some overlap, but it should be, in my intention, limited. Okay. So I clicked on the first link. Just 1 second. This one. If you look on the screen is still shared, yes. So I clicked on this link, and this is a web page which is actually it's an interactive presentation. It's not a web page. This is a new experiment that I decided to make this year for the first time. So let's put it full screen. Given that it's a new presentation, I discovered this morning there are some typos. I will highlight you and some issues that need to be corrected. And just give me the time to correct it. It's not a problem, but we can, of course, we can use it anyway. Let me check if, okay, good. Okay, so this is an introduction. And let's jump to the first slide. So let's focus on the left graph. It's global temperature at monthly time scale. Monthly time scale, global temperature from 1850 to today. It's up to December 2022. It is taken from this link, Our World in Data. Let me open it. You see the same graph in Our World in Data. There are a lot of data in this website. It is well referenced, so it's a good source of information. A lot of data, and let me just give you an example. Data Explorer. This is not what I wanted to click. Just 1 second, because this is CO2 data explorer, and let me, okay, here. This is the main page. And articles by topic. Okay, this is the list of the data they have. Demographic change, health, food and agriculture, energy and environment, innovation, poverty, economic development, etc., etc., etc. Violence and war, education and knowledge, and there is, of course, energy and environment. And if you highlight, there is a lot of information. So I clicked on climate change, and clicking on climate change, you get to the web page which I have shown to you before. And this is the global warming monthly temperature anomaly. Anomaly means that it's computed with respect to the long-term average. The long-term average is taken as the zero, okay? And it shows the deviations, the changes from the long-term average. And it's possible also to see, you see sea surface temperature anomaly, ocean heat content, top 700 meters, and with different oceans. Oh no, this is different sources of information, sorry. And sea level rise. Look at sea level rise just to give you an information and compare, to give you food for thought. Look at sea level rise and compare with the temperature anomaly. You see, it's a different behavior. It's a different behavior. There is no perfect correspondence between increase of temperature and sea level rise. The time scale is more or less the same. Oh, it's the same, I think. Yeah, it's not up to 2022, but it is more or less the same. And there is a big difference. And also look at the order of magnitude, starting from minus 200 millimeters, minus 20 centimeters, to plus 5 centimeters, okay, more or less. Okay, so this is the order of magnitude. When you look at science, just get aware of the orders of magnitude, because science is based on evidence. So when you talk about numbers in science, the first thing that you don't have to miss is the order of magnitude. If you discuss with a person and you make a mistake, a big mistake on the order of magnitude, then your credibility goes down. Okay, so when you talk about climate, and for instance, you talk about increase of global temperature of the Earth, and you don't know what is the average temperature of the Earth, I'm sure that probably you don't know, because I tell you, I didn't know what was the global average of the temperature up to 5 years ago, maybe. And then if you say just +1, because +1 is the effect of global warming, but +1, what does it mean? If you don't have an idea of +1 with respect to what? So the global temperature of the Earth, we will discuss it, it's about 14 degrees. So +1 is not really negligible, +1 over 14. If it was like 40 degrees, +1 over 40 is a different story. So the orders of magnitude are extremely important when you talk about science. Okay, I'm not sure about the other disciplines in humanities, if what could be a comparison of something of general information that is essential. In science, it's the order of magnitude. Okay, so a lot of interesting data here. So my message for you is, look at this, our world of data, in data. It's extremely interesting. Not only about climate. For instance, if you're interested in seeing equality of opportunities, diversity, or education, or democracy, it's interesting. There are several interesting information, and it is well referenced. It's a reliable information. Okay, let's go back here. So, graph on the left. What is clear here? Temperature is increasing, and there is no doubt on that. This is an evidence. This is something that is evidence-based. It's not an opinion. Temperature is increasing. From when? From 1850, after the start of the observations. Okay? Problem here. Unfortunately, we have the so-called instrumental period, the period along which we have observations on temperature that starts only in 1850. This is a big issue. Our knowledge of climate change, our awareness would be completely different if humans started to measure temperature 1,000 years ago. Unfortunately, we have measurements only from 1850. This is the so-called instrumental period, 1850 to today. And you may say, yes, but there are also information from the past. Yes, through proxy data. We will talk about this. And proxy data is not the same as observed data, unfortunately. Because, for instance, the time resolution is different. 3 rings are a good information at annual time scale. They don't give monthly temperature. But during this instrumental period, what's happening is clear. And especially in the past 30 years. And again, sorry if I insist, there is no doubt on that. You know that climate change is a controversial problem because there are different interpretations. This is not controversial. This is a fact. Everybody agrees on that. Okay, there is an increasing trend. Okay. Okay, this is a bit of a problem. Of course, we have to be able also to understand that it's not a problem for everybody. For some countries is more than a problem, for other countries is less than a problem, but it is something that it's evident. Let's look at the right graph. What is this? This is, again, from our World in Data. Global freshwater use over the long run. The same, not really the same period. This is from 1901 to 2014. Let's see, I think yes. Or let's do like this. No, in this way, no. Okay, let's do this. I don't think it's possible to zoom here on the screen, and in the PC I am already full screen. Sorry? Okay. Yeah, okay, I understand what you mean. Sorry. It was just 1 second. Sorry, I understand what you mean. It is this one. Anyway, given that now let me stick on the other. Okay, I think this is enough. So what you see here is impressive, and it's you see the global use of fresh water is increased a lot after the Second World War. This is due to the so-called Great Acceleration. We will talk again of the Great Acceleration. Great Acceleration in what? In societal development. After the Second World War, there are several indicators of the Great Acceleration. You can look at demography. You can look at freshwater use. You can look at a number of dams that were built to store water, because of course, if you have to cover this increasing use, you have to store water. And therefore we built a lot of dams. There are several indicators. And the question is, are these two graphs connected? Probably yes. Probably yes. It's clear that in correspondence of the Great Acceleration, there was an increase of temperature. It's also clear that there was an increase in the human population all over the world that is in the same way impressive. It's impressive as well, okay? And this is the identity card of the problem of sustainability at large. Sustainability and climate change are tightly connected. Any question? Yeah, there is a question, please.
Did you get to the 14 Celsius? That is the zero of that graph.
Okay, so the question is, I don't understand what is the zero of the graph. So the zero is the long-term average, which I said is about 14 degrees Celsius. Did I answer your question? Yeah, okay, good. Other questions? Okay. An interactive slide. Can I ask you a question? So what is climate change? Select the most appropriate answer. I'm sorry that there is a bit of overlap with the Zoom labels, but what you can, first of all, this is available to you in your laptop, so you can try your answer now or you can try later. So what is climate change? Select the most appropriate answer. Why I am asking this question? Because in my experience with several students, but not only students, also with several actors, I found that there is not yet a clear perception of what is climate change, of what we mean about climate change. There are some persons confusing the terms, the concepts of change and variability. And there are some questions that some people that are not aware of the difference of what is climate and what is weather. There is a fundamental difference between climate and weather. So let's try to learn this with this interactive way. So what is climate change? First of all, I would say that we cannot say that any one of these questions is wrong. The challenge is select the most appropriate one, okay? We could discuss if there is one question that is completely wrong here. But first, let's identify the most appropriate one. So it's a global deterioration of climate, or it's the occurrence of unprecedented extremes. It's a long-term shift in weather patterns. It's a global increase of temperature. Just 1 second, because I see that there is a raised hand. I would say that if you have any question, Ilaria, you can ask it directly. Let's try.
No, I would try to respond a quiz.
Okay, give your answer, please.
I think the keyword is long term. So in my opinion, the right answer is climate change is a long-term shifts in weather patterns.
Okay, and we assume that you didn't try to check at home.
yeah, I tried, but I think that long term is the right answer, because climate change includes extreme events, but not only temperature.
Okay, this is interesting, and thank you very much, Ilaria.
You're welcome.
Somebody has a different opinion on that? Okay, so as I said, I don't want to embarrass you, so let's try to click on it's a long-term shift in weather patterns, okay? Good, it is the correct reply. And here there is a comment which is out of place, okay? So forget about it for now, because it was a mistake by me. Or let me say, you will find the opportunity to discuss this comment later on, okay? So just forget about it for now. Okay, let's go back 1 second to to the question. So let me see. I think I could. I think there is the opportunity to repeat it, but let's forget about it because I don't forget. I don't remember what is the key to. Let's see. Yeah, probably you are right. And good. Thank you. Okay, just 1 second. Now. It's the occurrence of unprecedented extreme events. Not really, because we cannot really say that climate change necessarily implies that there are events that are occurring today that are unprecedented. I want to give you an example. During 1940 and 1950, in the north of Italy, there was a very heavy drought. And it lasted for 5 years with minus 20% precipitation. Such an event is still, in the instrumental period, the worst drought that we experienced in northern Italy. It didn't occur today. If we look at the drought that occurred after 2000, they are heavy, but not as heavy as the 1940, 1950. So not necessarily, I think, also, if you look at the temperature over the Earth in very old past, billions of years ago, it was higher than now. There were other periods in which the Earth didn't have any ice cap. Okay, so we cannot say that it's just the occurrence of unprecedented extreme event. Global deterioration of climate. If you go in Sweden, some people would tell you our climate is improved after climate change. Because they have less frozen soil, they can rely on some more extended agricultural cultivation. So they wouldn't agree that it was a deterioration. They would agree that it's a change, but not necessarily a deterioration. Of course, if you go in the south of Italy and also in the north of Italy, we say it's a deterioration because we get less water and we get more evaporation. So it's a problem. But we cannot say it's a global deterioration. It's a global increase of temperature, that's true, but not only that. So it wouldn't be a good definition. What is essential here is what Ilaria said. It's a long-term change, long-term shift. It's not just in 1 year. So 1 year doesn't make climate. But what we can observe and what we associate to climate change is a shift in the patterns of weather in the long time, like the graph that I showed to you before. Okay, so if you look at, temperature here, you see that there are short-term changes, but what is striking here, what is worrying is the increasing tendency of temperature from 1960 to today. And what is even more concerning is the rise, the sharp increase of the trend in the last 30 years. So you may say, yes, but if I look at the last part of the graph, the past 2 years, there is no increase of temperature. So why to bother about climate change? I would say 2 years is not climate. You cannot say that the global warming has stopped because in the past 2 years, we didn't get any record-breaking temperature at the global level. Actually, 2022 was the sixth year, the sixth warmest in the global. So it's still very warm, but it's not the first one. But the fact that it's the sixth doesn't mean that it stopped. You have to look at the long term. So now this discussion brings to our second question in this slide. What is weather? What is climate? Okay. And here the exercise is to complete the definition by placing 3 missing words. climate, one occurrence, and weather, two occurrences. Okay, so let me do it. Weather refers to the day-to-day state of the atmosphere, okay, like the combination of temperature, humidity, rainfall, wind, and other factors. Climate describes the weather of a place averaged over a period of time, often 30 years. So 30 years is the length, the conventional length of the climatic window. You may also say 10 years is fine. 30 is adopted conventionally as the usual length. Sometimes I prefer to refer to shorter windows, like 10 years. Usually, if you refer to less than 10 years in science, you get criticized. Okay, we may check. Everything is correct. And here you see a comment. Think about it this way. Climate is something that can be expected to happen in general, like a cold winter season. Even a full season can be considered climate. If you refer to seasons, you can use also the word climate for a full season. Like, it is a cold winter is a climatic statement. Can be interpreted as a climatic statement, even if it doesn't refer to 30 years. But I just want that you get used to be flexible. I mean, you can say, you can accept as a climatic statement a cold winter. Weather is what a person might experience on any given day. So, like a snowstorm in January or a sunny day in July is weather. And I also like to give this suggestion. Weather is an observation, climate is a statistic. Okay, statistic, what is a statistic? The average. The pattern is a statistic. Okay, so I think it is a useful suggestion. So climate is an observation, and an observation is not climate. So if we get 30 degrees in January in Bologna, it's concerning, but it's not climate, it's weather. Okay, if we get an average winter in Bologna of 15 degrees, an average temperature, it is climate. Because it's an average temperature, average is a statistics. Okay. Keep in mind that in science, definitions are extremely important, okay? When you talk in the communication with the public, definitions are less important because it is more important the meaning of what you say. And it is more important the message that you convey. In science, a definition is very important. You cannot interact in science with a clear definition, a clear set of definitions. Definitions are the basis for a theory. Okay, so we have to understand what is climate, what is weather, basically. It is not difficult. Keep in mind that this can be this slide is posing two perfect questions for a quiz. Okay, what is climate? How would you define climate? 7 alternatives. This is an ideal question. For sure it is there. Okay, maybe that you don't get it because the quiz is only 30 questions. I have a bank of a deposit of questions that is counting about 100. So given that they are picked up by chance, maybe you don't get it, but be careful because definitions are also very good topics for questions. Okay. Now, what is variability? What is change? Unfortunately, climate is not constant. Climate is variable. It's also changing, and the climate is also changing for natural causes. But what I want to be clear about here is the difference in variability and change. So The graph is showing two series of temperature for the same time scale: Northern America, average temperature, and tropical America. Okay, and you see that both of the series are showing an increasing trend. But the trend is more evident in the red time series, in the red record. In the blue record, you can still see the trend, but variability is a bit confusing it. It's a bit masking it. Okay, and think of a situation where the variability is even higher. It becomes distinguished between the trend, the tendency, the pattern, the long-term shift, which is change, and variability. It becomes difficult. And given that the climate is variable and is variable with different features, we need to perfectly understand what is variability, what is change. Okay, and variability, it is, look at the definition here. It is how spread out or closely clustered a set of data is. Okay, good. So it means that you see, it's the blue series is spread out. Change is the already defined long-term shift in patterns. In the presence of variability, as I said, recognizing change is more difficult. Variability makes it possible that in the past climate, before change, you got an extreme that is higher than what we get now under change. When I mentioned the drought between 1940 and 1950, of course, in the natural climate, there is some variability that caused this drought before climate change, before global warming, to be more impactful with respect to the last droughts that we experienced in the recent past. Okay, so beware of variability definition, and also the fact that we have to be quite careful when we see some strange weather, because weather is more variable than climate, because variability typically increases when you shorten the time scale. If you compute an average over 30 years, you average out part of the variability. There is still variability, but less than what you observe day to day. So be careful. Sometimes you get statements like, today is too warm, this is climate change. This is not a scientific statement, because one day doesn't make climate, and one day is maybe the effect of variability. It is important that we are precise in our statement, we are rigorous, because you know how it works. If we raise several alarms and then the alarms are ill-based, then the credibility of science is undermined. So we have to be very rigorous. Okay. Another question, and I want to tell you a story why I put this question there. Last year, I invited a colleague, he's a distinguished climatologist, he's a glaciologist, to deliver a lecture here. And he is intimately convinced that climate change is the biggest issue today at the global level for humanity. He's intimately convinced that we have already passed the limit, and intimately convinced that it is human-induced. He's really an advocate for that. And he started the lecture by asking this question. So first he asked the students, raise your hand if you are convinced that humans are causing climate change. And everybody raised their hand. And then he said, why? Can you please tell me why? So why you are convinced of that? And these are some of the answers that were given by the audience at that time. And Also here, there is the answer that you gave us correct, which the audience didn't pick up. So, do you have any idea of why humans are causing, why we are able to say humans are causing climate change? And you can have also a different answer with respect to what is reported here, and maybe also correct, because not necessarily the correct answer is unique. Any idea? I tell you that
Maybe the first in the graph we can see the hockey stick that represent the increase of temperature is very speed.
Yeah, okay.
Confronting to the past.
This is a possibility, yes, of course, the first one. Any other idea from the audience here? Yeah, there is a raised hand, please.
I think the second is the correct answer. Since we talk about statistics, we can forecast the future climates by looking at like there are some things that we cannot explain, so we should put anthropogenic forces into consideration to be able to understand the future properly. So yes.
Other opinions? Okay. Let's try the second one, which is the correct one. You picked it. Okay, now let's go back, given that we learned how to do it. And let me make some comments. So the reply, first of all, I voted for the first one when my colleague asked the question. So I was wrong last summer, okay? And he said, no, if you look in the far past, during the interglaciation periods, there were the proxy data tell us that there were periods where the temperature increased faster even than what we are experiencing today. I didn't know that. And then he showed a graph, which I think I put somewhere here. So he said, no, natural climate can vary also with the same speed. For the second question, he said, and I agree, science is not about consensus. Science should be evidence-based, not about consensus. It is a statement that is somehow tricky, because I think that at the end of the story, science is also about interpretation. And it is true that science should be objective, but there is room for interpretation. So, but basically I agree that it's not credible to say that something is true because there is consensus of scientists or consensus of the media. And we can make several examples where consensus in science was wrong. Think about Galileo, think about Copernicus. There are several examples. And you know that Galileo was forced to apologize because of his theory. And he was rehabilitated only after, I don't know how many years, but you may have heard last summer that the Pope, for the first time after 500 years, officially apologized with respect to Galileo. So, I mean, basically I agree that consensus is not enough. And therefore, my colleague said, look, the only evidence we have about the human influence of climate change, and he said, which I am intimately and firmly convinced it is a truth, is given by models, is given by our mechanistic understanding of processes. So models are clear. If you force them with increasing CO2 emissions, they provoke an increase of temperature. This is the only evidence. I was a little bit surprised because it is a good evidence, but still, of course, it is something that is still not based on observations. It's based on a theory. And anyway, I'm diving something more on this. But before that, let me give you some numbers, which I think are extremely important, and then we make a break, for giving you the order of magnitude. Some numbers. Global temperature has raised about 1.3 degrees Celsius since 1880. Temperature increased more in the northern hemisphere. In the past, during other warming periods, it was the opposite. It's not really clear what is the reason of the highest increase in the northern hemisphere. Keep in mind that this is a measurement that is based on ground measurements, and in the southern hemisphere we have less ground measurements because there is the ocean. There is dominance of the ocean. On the other hand, if we measure temperature with satellites, the increase is a little bit less than 1.3. Is like, if I remember well, 0.9. The Alps are an hotspot. It's not written here. In the Alps, the temperature has increased about 2 degrees. Why? It's not clear. Sea level rise, we already talked about it. It's about 21 centimeters of global sea level rise, global average from 1880 to 2020. Global CO2 emissions, they have raised a lot, 7 times, from about 5 to about 35 billions of tons from 1940 to 2020. But if you look at the global emission per capita, they have increased just twice. Just, it's not really the most proper word. They have increased twice, which is still relevant. On the other hand, of course, the increase in global population from about, look at the red circle, 2.5 billions in 1950 to 8 billions today. Clearly, an increase in global population means an increase in human emissions. But they are also increased, doubled per capita. CO2 concentration in the atmosphere increased about 25% from 1980 to 2020. Global economic losses from weather catastrophes. And be careful of what is written here. It's written weather catastrophes without any reference to climate change. So it's not global economic losses caused by climate change, which would require a longer discussion. But it is relatively easy to monitor the losses, global losses from weather catastrophes, because there is no, the attribution problem is very easy. Weather related is easier than climate change related. And it's about 300 billions of US dollars, and annually, oh, let me see. I don't remember this. I need to check. I will tell you later. Steadily increasing over time. These are facts, objective things, objective evidence. Now, I'm now making the break. An important thing to say. I will leave the video running with the camera and the microphone turned off, because otherwise it's very easy that I forget to restart the recording. So you will find in your videos 15 minutes of silence, just to inform you. Okay? Good. See you in 15 minutes. Okay. So let me start again. Sorry, I was a bit late because I got some questions from some of you. So what is IPCC? IPCC is another very good reference for you to get information on climate change. IPCC is the Intergovernmental Panel on Climate Change, and it's a body of the United Nations, and is charged with the mission of assessing the science related to climate change. IPCC publishes a lot of reports, and in particular, they have periodic assessment reports. They are called AR. So starting from AR1, and they just issued the AR6. These reports, as I said, are a very interesting reference for getting the latest news about climate change. It's not the only one reference. It's not the only one scientific reference. Keep in mind that the science about climate change is very prolific, is evolving over time. So you may find also different repositories for getting information about science. IPCC in general is not providing data, it's just providing an assessment of science. For data, you have to look at other repositories like, but I will mention it later, the Copernicus Data Store, which is a repository for getting climate data and the climate projections. IPCC, if you look at the reports, you see here a series of links dedicated to the AR6, Climate Change 2023. And if we click on it, here is the report. And by clicking again on the report, you get here, and I think that we should be able to find somewhere the quick links. Just one second. It's always difficult also. I found it in the morning, but I still have to think about it. So report, okay, let me see. I think it is this one. Yeah, this is the 6th assessment report. And here, again, if you look at the reports in detail, just one second, working group 2, you find here, physical science basis, okay? Summary for policymakers, downloads. Finally, we get to it. Okay, so the reports of the IPCC, I focused on the physical science basis. There are other chapters, and you may have a look if you are interested. And about the physical science basis, you have an extended report and a summary for policymakers. The summary for policymakers has an advantage. It's synthetic, it's a summary. And for getting preliminary information, I suggest, unless you are very interested in the physical details, in the details of the theory, to look at the summary for policymakers. If you look at the summary for policymakers, you get one of the first draft, one of the first discussion is about the current state of the climate. And there are some statements with a degree of confidence. So for instance, here you read, it is unequivocal that human influence has warmed the atmosphere, ocean and land. Widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. And if you look at the details, you see that after the bold statement, there are details, A1.1, and they specify what are the evidence, and very important, at the end here, you see the level of confidence. Okay, what does this mean? Level of confidence means the extent of uncertainty that is still related to these statements. And keep in mind, this is IPCC, so it's the voice of the United Nations. So in this case, you read carefully what's written there, and you get an indication of the confidence. If you want to be very scientific, you shouldn't extend to the statement. You shouldn't extend to other issues. Okay, so what's written here? Let's read just to realize what I mean. Observed increases in well-mixed greenhouse gas concentration since around 1750 are unequivocally caused by human activities. Since 2011, concentrations have continued to increase in the atmosphere, reaching annual averages of 410 parts per million for carbon dioxide, and then other details for the other gases. Land and ocean have taken up a near constant proportion, about 56% per year, of CO2 emissions from human activity over the past 6 decades, with regional differences, high confidence. Okay, so the high confidence is related to this statement. And then you can move forward, and there are other statements, and sometimes the confidence is lower. Okay, and this is extremely important to notice. Okay, here there is again high confidence, but let's see, high confidence, medium confidence. So there is, let's read this sentence, another example. There is high confidence that oxygen levels have dropped in many upper ocean regions since the mid-20th century, and medium confidence that human influence contributed to this drop. Okay, medium confidence, the meaning is clear, okay? And there is also another degree of confidence which is lower than medium. It is extremely important for what I'm explaining later that you keep in mind when you talk about science, what is the level of confidence of the evidence, okay? Let's move forward, and you see a graph here. Human influence has warmed the climate at a rate that is unprecedented in at least the last 2,000 years. And this is not in conflict with what I stated before, that in the far past, billions of years ago, there was warming that was higher than today. I was referring to the far past, not the past 2,000 years, okay? And this graph is reported also here in my slides, precisely the same. And here there is the reference. On the right, there is the reference. Now, what is telling this, these two graphs, what are they telling? So, on the left, you see change in global surface temperature, decadal average. Okay, so it means that the reference window is 10 years, has reconstructed 2000 and observed 1850-2020. Okay, so it is a reconstruction of past climate. On the right, there is change in global surface temperature, annual average, as observed and simulated using human and natural and only natural drivers from 1850 to 2020. So two things to say. First, the left graph is a reconstruction of the past temperature for the past 2000 years. And there is, you see, a shaded area. What is the meaning of the shaded area? The meaning is to quantify uncertainty, which is related to using different proxy data. And you see that also there is a thick line, which is the average along 10 years. So there is uncertainty in the reconstructions. Still, the recent warming, it looks like, even if you consider uncertainty, is unprecedented in the past 2000 years. Okay. Graph on the right. It's a reconstruction from 1850 and using models, not proxy data, models. Okay, climate models can be used to simulate also the past. Okay, and the simulation can be done by using the drivers related to the real drivers of emissions, including the human emissions, can be done by subtracting the human emissions. And what this simulation shows is that if you don't include the human emissions, you cannot explain the recent warming. So this is the evidence that I mentioned to you before. This is related to models, of course. It must be clear, like my colleague said, it's models, okay? So if you use these models, which reflect the best of our knowledge, you cannot simulate the recent warming unless you include the human emissions. Why the shaded area in this case? If I use a model, it should be like a unique line. Actually, we are using different models, several models, because there are several models available, and they reflect different theoretical structure, different theories on the functioning of the climate, and different initial conditions. For instance, what are initial conditions? When you launch a mathematical model, whatever it is, you have to start from a starting point, which means that you have to give data on the state of the system that you are simulating. Like if I want to simulate tossing a coin, I should say what is the position of my finger when I toss the coin. Okay, if I toss the coin here, is different than tossing the coin here. This is the initial state of the system. And models need to know that. But in 1850, when we start the simulation, we don't know the initial state of the system. So we have to guess. And for different guesses, you get a different response, even from the same model, and then from several different models. So you get a shaded area, which is uncertainty. The shaded area is quite relevant in extension, because if you look, for instance, at the brown shaded area in the recent past, it goes from 0.7 to 1.7. So it's about 1 degree. It's very significant. Still, it looks like, even if you look at the lower bound of the brown shaded area, it is above the upper bound of the green shaded area. So it means that even in the presence of uncertainty, it looks like the response of the model is clear in attributing to the human influence the effect on climate. This is about temperature. We are not talking about other climatic variables, and this is global temperature. Now, keep in mind that model uncertainty, whatever model you use, and I hope that those of you who are not, between commas, pure scientists, don't get depressed by the word model. I mean, we can use model in any discipline, even in humanities. We use model every time we make a prediction. It's just a way, a formalized way of elaborating a prediction. Okay. These models that we use to make predictions, which we use every day. Okay. Like when we look out of the window to understand whether we have to take an umbrella when we leave from home, we are using a model. This is a perceptual model, it's not a mathematical model, but still is a model. Okay. In climate, they use mathematical models. I'm not a climate scientist myself, so I hope that I can be clear enough. They use mathematical model, but it's no difference conceptually from a perceptual model. Okay, now these models, the uncertainty of these models, which we may use, depends on two important behavior: the time scale and the spatial scale. Just remember this, it's not written here, but it depends on the time scale and spatial scale. What do I mean with this? If I look out of the window and I elaborate a perceptual model to understand whether it will rain, it is working well in the place where I'm living. But if I have to travel, I live in Reggio Emilia, I have to travel to Bologna to teach, the model may fail because it may be a good weather in Reggio Emilia and a bad weather in Bologna. So the spatial scale means a lot. So a model can be reliable on a spatial scale, on a spatial point, not reliable at another spatial scale. So this uncertainty refers to global temperature, okay? It doesn't mean that for the Alps we have the same uncertainty. Typically, the lower the scale, so from global to continental, the higher the uncertainty, typically. When you average over a large extent, you decrease uncertainty, typically. This is for the spatial scale. Keep in mind, it shouldn't be a term that looks hostile to you. Spatial scale means location and extension of the validity of your prediction understanding, okay? We talk about fine scale when my model, my prediction works here, but not there. We talk about large scale or global scale when my prediction applies to a large area. So keep in mind, models work at different scales. When you look at the average, global average, you get one uncertainty. When you look locally, there is another uncertainty. The time scale, we already spoke about it. The time scale is the extension over which I average my prediction. So if I want to make a prediction of the weather tomorrow, I'm working on a daily time scale. If I make a climatic prediction for 2100, I'm working on a decadal time scale, tens of years. When we change the time scale, uncertainty changes, and sometimes also we have to change the model to elaborate our prediction. We will have a lecture dedicated to climate models. I just want to give you an idea of what models are and what uncertainty is. Now, let me delve a little bit more into, just 1 second, I'm skipping this, about uncertainty. What is uncertainty? We have to define it without any reservation. Uncertainty is normal in science. As I said, when we communicate it, we have to be careful. But uncertainty is normal. And on the left, you see a picture of a turbulent process and a chaotic process. I'm sure that you know the paradigm that was introduced by Lorentz on the butterfly effect. Like a butterfly that flaps in Japan causes a tornado in the United States. It's a very nice example of chaotic behavior. It doesn't mean that the butterfly has the energy, releases the energy for the tornado. It's just that the butterfly changes the initial conditions of the model. And this brings back to uncertainty. As I said, different initial conditions of the state of the system cause uncertainty. A butterfly flapping in Japan then changes the initial condition of the model that extends from Japan to United States and can cause a tornado, because the energy that is already available for the tornado is triggered in some way. Okay? And chaos and turbulence are essential component of environmental processes. of nature. Nature is chaotic. And chaos means uncertainty. Okay? Let me give you a very simple example. If I toss a coin, the process is perfectly known, is dictated by the laws of physics. Okay? It's completely known. I can describe it with mathematical equations. Just 1 second, I close the door. Now, if everything is completely known, why I am not able to predict the outcome from tossing a coin? Because a small change in the strength of my finger, a small change in the position of my hand, a millimetric change can change the result. Why? Because I change the initial condition of 1/10 of a millimeter and the result is different. This is chaos. A small change in initial condition when I toss a coin or when I toss a die makes the process unpredictable. But in statistical terms, it's perfectly predictable because I know that I can have either head or tail. 50% of the times I will have heads, 50% of the times of the trials I will have a tail. So the process in statistical terms is perfectly predictable, but with uncertainty. So uncertainty is not a lack of knowledge, not necessarily. It's an intrinsic behavior. So we shouldn't be discouraged. We shouldn't be depressed or to hate uncertainty. It's essential. And once that we can estimate it, it allows us to make design, to devise strategies. It's not a problem, but we have to be aware of it. Now, here there are questions and the reply, maybe you can understand already what is the most correct reply. So what is uncertainty? And there are some statements. What is the most appropriate? Uncertainty can be eliminated by improving scientific knowledge. Uncertainty means limited predictability. It's not necessarily due to lack of knowledge. Uncertainty is caused by imprecise information, theory, data. Uncertainty is caused by limited knowledge, which in turn implies that predicting models are wrong. So, what is the most appropriate answer? I don't want to. The second, of course. The second. And uncertainty indeed means limited predictability, even if the knowledge of the process is perfect, but not unpredictability. Is limited predictability applies also to tossing a coin. By the way, tossing a coin is much less predictable with respect to climate, just to be clear. But still, we cannot predict climate with certainty. We cannot say that in 2100, we will have an average temperature that is like that. IPCC doesn't say that. IPCC says with high confidence, I have, in 2100, I will have a given temperature, okay? And here there is the example of tossing a coin. Okay, so we will talk about uncertainty. And again, let's try to be constructive about it. It doesn't mean that we cannot do anything. This is a destructive approach. Like when you want to stop an action, then you may say, okay, science is not clear, science is still uncertain, the IPCC doesn't have a full confidence, it's medium confidence, so let's do nothing. Okay, this is a destructive approach. We have to avoid this, but on the other hand, we cannot make we cannot design any action if we don't estimate uncertainty, because otherwise we run the risk of being completely wrong. And I make you another example. I recently submitted a paper which is still under review and was a bit criticized. In science, this is normal. I mean, when you submit a paper and it's criticized, it's not necessarily a bad thing. It means that there is something in it that is picked up. And what I have basically shown is very simple. Now we have here in this region the problem of droughts. you know, and just yesterday you have seen the newspapers, the Po River, again, a problem. At 6 o'clock in the afternoon, I will give an interview to Salo News. Do you know about Salo News? I didn't know about it. It's a recently launched application for delivering news online. And it was advertised also by the newspapers, by Repubblica, Corriere della Sera in Italy. And they asked me to release an interview on the drought of the Po River, okay? Because, you know, it's really a concern. Now, the paper was about this. It was, okay, the droughts are a problem. Let's take climatic projections up to 2100 for the Emilia-Romagna region, and let's estimate the risk of drought under the worst possible scenario, okay, in terms of emission, etc. And then let's take the traditional way of doing it. I take observations from weather in the past, and I take the worst event that occurred in the last 100 years, and I take it as a critical event, okay, critical situation, like what happens here if in the drought between 1940 and 1950, sorry if I again mention it, I assume that it repeats in the future. And we made the comparison with the climatic projections. Unfortunately, what comes out is that the climatic projections are more conservative. So if we adopt the climatic projections to estimate the chance of a drought today, it is, sorry, I was wrong. It is not precautionary, it's not conservative. It's much better to look at the observations at the most critical event that occurred in the past. So my conclusion was, let's be careful. We don't have to trust models, especially for droughts, as they were perfect. We have to be critical. We have to be, otherwise we run the risk of making a mistake. We have to be aware of uncertainty. Otherwise there might be a mistake. This is not to say that models are wrong. Absolutely, models are perfect. But for some scales, some locations, they may be not pessimistic enough. Okay, so this is the message that I want to convey. Let's be very careful about uncertainty. The problem is indeed very, I mean, look at I'm sorry that it's not, let me just, okay. Let's look at the title of the slide here, because if I make it full screen, it's not clear. Water-related disasters are the most impactful climate-related events. And of course, here we are using a definition of water-related disaster that is quite extended. So let's look at the graph. 2022, just a few days ago, during the year, what were the most impactful disaster related to climate? The Hurricane Ian in Cuba. I would say that it is classified as water related, but I wouldn't say that. I think it's less water related with respect to drought and floods. But then you see only floods and droughts in the list, with the exception of another hurricane in the Caribbean, in Canada. So this means that floods and droughts, I mean, they are a big issue. And so this is why very often I make this example. I am a water scientist. I am also a bit biased, but the data here are clear. This is an evidence. So but on the other hand, here there is another question. In your opinion, is the frequency of floods increased at the global level? This is a truth. If you look, there are some data on the web which are given by the insurance sector, which show to you global statistics and regional statistics on the damage induced by, let's call them natural hazards. Natural in the sense that they are related to nature, okay? And you see that clearly there is an increased impact of floods and droughts. So, select the most reasonable answer. Yes, it is increased for the effect of land use change. Yes, it is increased, but it's still not clear what the drivers are and what is their relative contribution to frequency raising. No, it's not increased. I just said that this cannot be correct. Yes, it is increased after climate change. So the answer is, sorry if I anticipate you, it's the second. There are several drivers, and we have to understand them. Flood frequency is increasing indeed, for the combined effect of different anthropogenic impacts. There is climate on the one hand, and there is also urbanization, river tunneling on the other end. River tunneling in particular is extremely relevant. Okay. On the other hand, it's clear, even if the data are still not very clear about that, but it's clear that there is an increase recently of extreme short time rainfall. What this means? There is an increase of the violence of rainfall with short duration. It's not so clear that there is an increase of the rainfall that lasts for 1 week, but it's becoming clear that for the rainfall that lasts like half an hour or 5 minutes, there is an increase. Unfortunately, the data are still not clear. Why? Because we have few measurements. It's easy to observe rainfall that lasts 1 week. It's not easy to observe a rainfall event that lasts 2 minutes. It's not easy. We have only few observations, but the perception is clear. Okay. So it is why it is important that we understand the drivers. So I get some colleagues and some students in the past who told me, let's focus on climate. Let's forget about land use change or river tunneling, because it is important that we convey to policymakers the message that climate is the issue. I understand, but once again, we have to make clear that what we say depends on the context. So I may agree that if the purpose of providing a communication is to convince an administration, a political party to take a given action, like reducing the CO2 emissions, I agree that it's not the point to mention river tunneling or urbanization, land use change. It's not relevant. But if the purpose is to avoid a disaster, so what happened in the Marche region, to avoid it, if the purpose is that, then we have to be very rigorous on the identification of the causes. If it is climate change, there is a solution. If it is land use change, the solution is different. If it is a combination of drivers, again, the solution is different. So this is why I insist, from a scientific point of view, we have to get the ideas clear. In my opinion, the role of the scientist is to convey evidence, the truth, and then it's another role, that of communication and action, political decision. It's another role. Of course, a scientist also should be able to communicate and should be able to adapt the communication to the context. On the other hand, let's not to forget that when we talk about be clear about the causes, there is a reason, and the reason is that we want to be effective in taking an action. So I want to give you a very clear example of what I mean, and I take the risk of being maybe inappropriate. I mean, I am convinced that there are some of the disasters that are occurring in Italy, and but I would say also in Europe, some of these disasters are related also to inaction, lack of preparation. And the lack of preparation I think very often is due to the fact that we blame climate change as an excuse. There are some administrators who understand that want to leave the responsibility, to waive the responsibility. And I understand that deciding what to do when a disaster occurs is difficult. And also keep in mind that whatever you do, there is a social cost, which for a politician is particularly important because it means also popularity, it means credibility. And I understand that sometimes they don't have the resources to take local actions. So for them, it's more convenient to invoke a global action. And but some of the disasters can be avoided with the local actions. So if there is a river tunneling that after climate change gives some problem, you may have two different solutions: remove the tunnel or changing the climate. If I was a local administrator and I am in charge of the responsibility for the lives of people, probably I consider removing the tunnel or not, because it is something that I can do. And also it is something that I can do now. This is adaptation to climate change. Removing the tunnel is adaptation. Changing the climate is mitigation. It takes longer. So we have to be very careful in what is the driver. So we already talked about uncertainty. Now, what is science? Let's just reduce a little bit in order to read the title. What is science? And I conclude with this slide. It is, we have to be very clear about that. Science is a systematic endeavor that builds on and organizes knowledge in the form of testable explanation. This is not my definition. I took it, I think, from Wikipedia. And predictions about the universe. Here there is a link. Let's see. It's Wikipedia, yes. The term testables is essential. Science is objective and its conclusions should be supported by testing and validation. Of course, it's not always possible. Had we collected more data on climate of the past, validation testing would be easier. Given that we have only a few data, sometimes it's not easy. And this is why I say there is room for interpretation. But still, let's think at the definition of science. Leonardo did science in this way. He observed and proposed explanations and tested these explanations. Interpretation of testing and validation may be, however, subjective. And therefore, the history of science is started with erroneous conclusions. An illustrative example is Aristotle's convincement that Earth occupies the center of the universe. He was not the only one, by the way, but he was very firm in that and provided a scientific explanation of it. Okay, so let's conclude with this comment. Climate change involves several disciplines, and it is necessary that we adopt an interdisciplinary approach. I already mentioned that. We have to be interdisciplinary. Why? Because if we don't start interdisciplinary, what happens with climate change, unfortunately, is that we start from disciplinary conclusions, disciplinary propositions, but then we are fortunately living in a democracy. We have to discuss them with the stakeholders. And if it is disciplinary, then the discussion ends into a conflict. And the conclusion of this conflict, 95% of the time, maybe even more, is nothing. We do nothing. So an example, which is very, I think, significant. Okay, climate change is increasing the drought, the risk of drought. What should we do? So if I reason with if I think at it with my background and my expertise, I think we need more water, which means more storage, which means dams, artificial reservoirs. If I get into a discussion, into a public discussion, there are environmentalists and natural scientists which come up and say, no, it's not a good solution. It's not a good solution because there is an environmental impact. Another example are electric cars. Electric cars are the future, yes, but what about the batteries? How to displace the batteries? You know the problem. And so the result of this confrontation of opinions in a democratic context is very often that we do nothing. How to solve it? I don't think the solution is to impose a solution. Like, I want a dam, and I decide, I make it. And I don't care about any concern, any people that is flooded by the stored water. I make it. I don't think this is a good solution. The other solution is to start interdisciplinary. So the discussion should not be based on individual disciplinary premises. The premise should be interdisciplinary from the beginning. And actually, this question that I'm asking here is a bit provocative. Like, what is the most related discipline to climate science between these ones? I think the most related is the one that is considered, if you make a pool, the less significant. The most, here I am biased, but the most related one is hydrology. It's the science of the water cycle, because, I mean, water is essential for climate, is a driver. But actually, if you look at also the IPCC reports, you see that the expertise from water science is limited. And this means that there is a vulnus in the approach. It doesn't start from interdisciplinary, a full interdisciplinary basis. And I think that we can do much about this. We can do a lot. We can call for an approach that is diverse, inclusive, and equalitarian, which is extremely important. If we want to be effective against climate change, we have to adhere to EDI principles: equality, diversity, inclusivity, at all levels. Good. Do you have any questions? Okay, so we will see each other again next Monday. And next Monday, if you have any question that comes to your mind, we can start with the discussion phase. Okay, good. Thank you very much.